Hello. In this lesson, we're going to go over the study of sequences. Now, sequences are important because eventually, after we study sequences, then this will lead to the discussion of series. And then after we have a good understanding of series, that will lead us into power series. And from power series, then, we will begin the study of Taylor series. Now, Taylor series are of particular importance because we can use Taylor series to write very common functions like sine, cosine, natural logarithm, exponential function e to the x as a series of polynomials added together. And so this is a very important topic in mathematics. So let's begin with a discussion of sequences. So here's our definition for a sequence. So a sequence is simply a function whose domain is the positive integers. Now, this is not strictly adhered to. It might not be the positive integers. It might include some negative integers. It might just be all of the integers. So this isn't strictly adhered to, but this is the definition that we're going to start with. So a sequence is a function whose domain is a set of positive integers. For example, consider this function f of n. Notice we use the letter n since n is only supposed to take on integer values. Okay, so we say f of n equals n over n plus 1 for n greater than or equal to 1. Now this will generate the sequence of numbers 1/2, 2/3, 3/4, 4/5, 5/6, and so on. Now the way we get these numbers, notice, is by plugging in 1, 2, 3 in for the n right here. So for example, notice that f of 1 equals 1/2, f of 2 equals 2/3, f of 3 is 3/4. So that's how we get this sequence of numbers, right? So these are the values in the range of your function f of n. Now notice oftentimes these sequences that we'll be studying, they look like just regular functions that we've studied before. For example, f of x is x over x plus 1. Now, we've studied functions like that. So all we're doing here to turn this into a sequence is we just restrict the x to only take on integer values. In particular, the integers 1, 2, 3, 4, and so on to infinity. Now here's some notation also. Sometimes you'll see a sequence written like this. Instead of using this notation, oftentimes you'll see sequences written using this notation a sub n to denote f of n. This simply makes it a little clearer that you're studying a sequence and not some function. Or you might see the sequence written like this, or just like that. You notice a sub n as n goes from 1 to infinity, or you may not even see the 1 to infinity included. It might just be written like this, or you might even see it written like this. You may say it written like that. So there are some different notations for sequences. Now let's take a look at what we mean by the graph of a sequence. So if we're given a sequence like the one we just looked at, n divided by n plus 1, for n being an integer bigger than or equal to 1, then the graph of the sequence is merely the set of these points plotted on the Cartesian plane. So for example, we would just plot these points. If n is 1, then a of 1, if we put 1 in here, notice we'll get 1/2. So we plot that on the Cartesian plane. If n is 2, a of 2 is going to be 2 over 3. So we plot 2, 2/3. If n is 3, a sub 3 is going to be 3/4. And so on. And so we would just plot these points on the Cartesian plane. And the graph of these points together will form the graph of our sequence, which looks like this. So right here you see this is the graph of our sequence. It's merely a set of dots plotted on the Cartesian plane, like that. Notice this is 1, 1/2. Right? The 1/2 is a sub 1. This point is 2, 2/3. The 2/3 is merely a sub 2. 3, 3/4. This is a sub 3, and so on. Okay? Now, if you were to graph the function f of x equals x over x plus 1, say for x bigger than or equal to 1, well, the graph of this function would merely be just like connecting the dots, right? All these dots would lie on the graph of this function. So the graph of f would, it would merely look like this, right? It would keep going. So you see, that's the graph of the function, is just this line, this continuous line, whereas the graph of the sequence, a sub n, like that, is merely the points that lie on this continuous graph. So if we get rid of that continuous graph, those points together constitute the graph of a sub n. So that's how we graph a sequence. Now here we have another example. Let's graph this sequence. A sub n equals -1 to the nth power divided by n. So you notice if we start plotting out the points n, a sub n, if we start plotting out these points, we generate these points right here. Notice 1, -1. That -1 is a sub 1, right? If we put 1 in here for n, we get -1 to the 1 over 1. Well, that's just -1. That 1/2 is a sub 2, right? If we put 2 in here for n, -1 squared is 1 over 2. The -1/3, that's a sub 3, okay? If we put 3 in here for n, -1 cubed is -1 over 3. And then this, of course, is a sub 4. So you see we have this alternating pattern in the range of these points, the range being the second coordinates or the y coordinates. Notice we have -1, +1/2, -1/3, +1/4, and so on. Okay, so down here is what the graph of the sequence looks like. So notice down here we have 1, -1, that point plotted, that's down here. Then 2, 1/2 is up here. Notice that the y coordinate here is positive, and that should be a 1/2 right there, not a 1, 2. And then down here is 3, -1/3, 4, 1/4. The next one would be 5, -1/5, 6, 1/6, and so on. And you see how we generate this graph. Now, in contrast to the previous example where we had a sub n being n over n plus 1, and we could think of this as just being the restriction of a function which we've studied before, like f of x equals x over x plus 1. You can't really do that with this sequence, because if we replace the n with x's, you'll get, and depending on this x value, the negative 1 to the x may not even be defined over the real numbers. For example, if x is 1/2, negative 1 to the 1/2 power, well, that's a complex number, but negative 1 to the 1/3, that is okay, that is defined, but then negative 1 to the 1/4 wouldn't be defined again, so we can't really represent this sequence as the restriction of a real valued function over the continuum of the real numbers. Now let's take a look at this example. So here we're given a sequence of numbers: 1/2, 3/4, 7/8, 15/16, 31/32, and we want to find a function a of n, a sub n, that generates this sequence of numbers. So instead of being given the a sub n and then being able to find these, we're given these and we want to go backwards and find what the a sub n is equal to. Well, what you have to do with a problem like this is you just have to do some pattern recognition. For example, if we look at the denominator of these numbers, we see the 2, 4, 8, 16, 32. Those look familiar. Those look like 2 to the n power, right? See, if I put in 1 for n, I get 2. If I put 2 in for n, I get 4. If we put 3 in for n, we get 8. 4 in for n, we get 16. So it looks like the denominator is being generated by 2 to the n power. Now the numerator, 1, 3, 7, 15, 31, you see all of these are just one number less than the numbers in the denominator. So the numerator is going to be generated by 2n minus 1. And so therefore we have our a sub n function, so we conclude that a sub n is going to be 2 to the n minus 1 over 2 to the nth power, and that's for n bigger than or equal to 1. And so you see, if we put in values like 1, 2, 3, 4 into this function, we will get these numbers back. Let's look at one more before we move on to the next topic. Suppose you were given this sequence. So here's another sequence of numbers. Let's try to find the function a sub n that generates these. Well, if we look at the denominator again, we see 1, 4, 9, 16, 25. Those look familiar. Those look like n squared, right? So it looks like our denominator is going to be n squared. Right, if I put 1 in for n, I get 1. If we put 2 in, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. And then we see the numerator is just 1 plus whatever's in the denominator. So this is going to be n squared plus 1. And there's our function that generates this sequence of numbers. Now let's take a look at convergence of sequences. So a sequence a sub n is said to converge to some limiting value L if, as n is taken larger and larger, in other words, as n goes to infinity, the a sub n terms get closer and closer and closer to that finite number L. So when that happens, we state that the limit as n goes to infinity of a sub n equals L, and that's the notation we use. You've seen notation like that before, of course. So for example, if you consider the sequence a sub n equals n over n plus 1, and if you write out a few terms of this sequence, you'll see you get 1/2, 2/3, 3/4, 4/5. You can see that these are converging towards 1, right? This is 0.5, 0.67, 0.75, 0.8, they're getting closer and closer to 1. And it's easy to see that in this case for this particular sequence, because if you consider n over n plus 1, notice that as n gets really large, this 1 right here doesn't really play very much of a role, right? So for n very large, this is approximately n over n, which of course is equal to 1. And so it's easy to see that the limit as n goes to infinity of this sequence is equal to 1. Now a little more precise way to do this, and we'll see down here when we look at some examples, if you think back to techniques that you've seen in Calc 1, where you looked at the limit as x goes to infinity of x over x plus 1. Remember how you did something like this? You multiply the numerator and denominator by 1 over the highest power of x appearing in the denominator. So in this case, let's just put the n's back in there. We would multiply this as follows. Right, multiply by 1 over n to the highest power of the n in the denominator, which is 1. Now just multiply these through and you get there you go. And of course, as n goes to infinity, this term right here is approaching 0. And so we see that our limit is going to be 1 over 1, which is 1, which is exactly what we thought it should be. And graphically, if you look at the graph of this sequence, here's what its graph looks like, just plotting out the points n over n plus 1. More precisely, we're plotting the points n, comma, n over n plus 1. Those are the points that are being plotted here. You see, these points are approaching this horizontal line y equals 1. They're getting infinitely close to it. And so in other words, the y coordinate of each of these points here is getting closer and closer to the number 1. So you can see that graphically as well. Now let's take a look at some theorems involving limits of sequences, and you'll see that these theorems mimic theorems that you've already seen when dealing with limits previously. Now, as I just mentioned, when you're dealing with limits as n goes to infinity of sequences, these will mimic the limit as x goes to infinity of functions f of x, and you've seen limits like these before. So all of the results that hold for limits as x goes to infinity for functions also holds for sequences. So that's what Theorem 9.1.6 is doing. It's just restating results for limits of functions that we've already seen. So for example, if you look at the limit as n goes to infinity of some constant times a sequence, you can move the constant out in front of the limit and just evaluate it like this. See that? Just move the c out in front of the limit, because the c does not involve the n, so it can be moved out in front, and you get your limit of this sequence is c times l. Okay, assuming that the limit as n goes to infinity of an is l. And you have results like this. Part 2 here, you see if you have the limit of the sum or difference of two sequences, that's going to equal the sum or difference of the limits. Notice you can distribute the limit into each sequence. That's basically what we're doing, and you end up with L plus or minus M, where L is the limit of the ANs and M is the limit of the BN sequence. Same thing for products. So in other words, the limit of the product of these two sequences is the product of the limits, and we get L times M. And the same thing for the quotient. The limit of the quotient of two sequences is the quotient of the limits. You see how you move the limit into the numerator and the denominator, and you get L over M, provided of course the M does not equal 0. Now we also have this theorem down here. If you have a sequence an and a function f of x, in which the a sub n terms are equal to f evaluated at n, then of course if the limit as x approaches infinity of f of x equals L, then the limit as n goes to infinity of a sub n will be L as well. And if the limit as x approaches infinity of f of x is plus or minus infinity, so will be the limit of the an terms. Now let's take a look at a few examples where we use these theorems. Now here in this example, we want to evaluate this limit as n goes to infinity of n squared divided by 3n squared plus n plus 1. Now you'll recognize that you've already done problems like this in Calculus 1, except instead of the variable n, you used the letter x, because you were looking at this as being a function of x over the continuum of the real number line. So in Calc 1, you evaluated limits like this. With simply an x in place of the letter n. Well, the techniques are going to be exactly the same for this one as opposed to this. So right away you might recognize, oh, since the degree of the top is the same as the degree of the bottom, they're both of degree 2, polynomials of degree 2, my answer is going to be the quotient of the leading coefficients, which in this case is going to be 1/3. And that is correct. It is perfectly fine to do that. Now let's take a look at some of the solution techniques here anyway. So if you recall from Calculus 1, what you can do when you evaluate this from Calculus 1, what you would do is multiply the numerator and denominator by 1 over n to the highest power appearing in the denominator. Now the denominator here, the highest power is 2, so you'd multiply the top and bottom by 1 over n squared. This is how you handled a problem like this in Calculus 1. So you see right here we start with our limit. We multiply top and bottom by 1 over the highest power appearing in the denominator, which is n squared. And when you multiply these through, you see you get 1 over 3 plus 1 over n plus 1 over n squared. Now as n goes to infinity, of course, these two go to 0. 1 over n and 1 over n squared go to 0. That's what we have right here, where we distributed the limit to the numerator and denominator. So actually going from here to here, we use part 4 of the previous theorem, which stated that the limit of the quotient of two sequences is the quotient of the limits, putting the limit in the numerator and denominator. So you see these go to 0 right here, and you get back 1/3. Now another way to do this problem is to use Theorem 9.1.7, where we simply replace this with a function of x, where x is allowed to be any real number. And when we do that, we can use L'Hopital's rule. So you see right here we replace the n with an x, and now we can apply L'Hopital's rule because this limit is of the form infinity over infinity. Okay, as x goes to infinity, both the numerator and denominator go to infinity. So we can apply L'Hopital's rule 2 times. So you see the first time we apply it, we get 2x over 6x plus 1. 6x plus 1 is the derivative of this. Now this is still of the form infinity over infinity. So you apply L'Hopital's rule again. Derivative of 2x is 2. Derivative of 6x plus 1 is 6. And now this limit, of course, is 2/6 or 1/3. And there you go. So you can use L'Hopital's rule. Now you notice when we did this problem, we replaced the n's with the letter x. That's because the n is supposed to only take on integer values, right? The n is supposed to only take on values like 1, 2, 3, 4, and so on. So it's not really proper to think of differentiating this function since the n is only allowed to take on discrete quantities. Whereas down here, the x is any real number. Now, it's perfectly fine if you leave the letter n in here like this, and then just think, okay, n is now a real number, any real number, so I can differentiate and use L'Hopital's rule, and so you just leave the n's in here. That's perfectly fine to do that. And you'll get the same answer, of course, just leaving the n's in there instead of changing them to x's. And then finally, another way to do this, which is what we've already mentioned here. You can recognize that since this is the limit as n goes to infinity of the quotient of two polynomials of degree 2, then from calculus 1 techniques, you know that this limit is going to be the quotient of the leading coefficients, merely the 1 over 3. Okay? And once again, another way to think of that is to think that as n gets really large, right? As n gets extremely large, the n squared terms are dominating, right? 1 million squared is much, much bigger than 1 million plus 1. So these two terms you can basically think of as not really contributing anything, eventually disappearing, and you see this is going to be approximately n squared over 3n squared as n gets very, very large, and of course this is 1/3, and that's your limit. So that's another simple way to think about the answer. Let's take a look at this problem. So here we want to evaluate the limit as n goes to infinity of the natural log of n divided by n. Now once again, we're going to invoke Theorem 9.1.7. We can think of replacing the n's with x's like this. And now evaluate the limit of this function as x goes to infinity right here. Now this is of the form infinity over infinity, so you can apply L'Hopital's rule. Right here, that's what we do. So you see we take the derivative of the top divided by the derivative of the bottom, 1 over x over 1. This simplifies as 1 over x, right? And then as x goes to infinity, this is perfectly fine to evaluate. You don't apply L'Hopital's rule again, and you get 0 as your answer. 1 divided by a very, very large number is 0. Okay, and that's your answer. And that's all you have to do for this one. Now once again, if you didn't want to replace the n's with x's, that would be perfectly fine. You could apply L'Hopital's rule to this. Just think of the n as being any real number, and then you can apply L'Hopital's rule and write this as the limit. And you see we have the same thing that we have right here, just with the letter n in place of the x. And once again, the only reason you'll see textbooks do this, replace the n with the x, is because technically you're supposed to think of x as being a variable that can vary across any real number, and the n's are supposed to be only relegated to the integer values, 1, 2, 3, and so on. So, technically you can't differentiate a function whose domain is only the integers. Now down here we have another example. So here we want to evaluate the limit as n goes to infinity of n cubed plus n squared plus 4n plus 1, so a third degree polynomial, and then in the denominator 5n squared plus n plus 3. Okay. Now from your experience with doing problems like this in Calculus 1, you can recognize right away that since the degree of the top is 3, the degree of that polynomial is 3, and the degree of the denominator is only 2, that this limit is not going to exist. It's going to equal either plus or minus infinity. Okay, so you could recognize that right away. But technically, this is how we do it down here. So you see right here, we start with our limit we want to evaluate. Now the degree of the denominator is 2. So we'll multiply top and bottom by 1 over n squared. This is how you did it in Calculus 1 when you had x's in place of the n's. This is exactly the same technique. When we multiply through by the n's, you see what we get is this is what we get for the numerator, and this is what we get for the denominator. Notice we get n plus 1 plus 4 over n plus 1 over n squared. That's what you get when you multiply this 1 over n squared against each of these terms. And then when you multiply 1 over n squared against each of these terms, you get 5 plus 1 over n plus 3 over n squared. And then by the previous theorem, we can move the limit into both the numerator and denominator right here. And now you see the limit of the denominator is going to be 5, right? Because the 1 over n, as n gets really, really large, the 1 over n is going to 0. And the 3 over n squared is going to 0. So you're left with the 5. Now in the numerator up here, both of these terms go to 0 as well. 4 over n and 1 over n squared. However, the n plus 1, that goes to infinity, right? As n goes to infinity, so does n plus 1. And so what you're left with is infinity over 5, and that of course is just infinity. A really, really, really large number divided by 5 is still a really, really large number. So it's infinity. So this limit does not exist, or in particular you can say the type of does not exist is that it's equal to positive infinity. Now in this example, we want to prove that for any fixed constant r, that the limit as n approaches infinity of 1 plus r over n to the nth power is equal to e to the r power. Now what we're going to do here is simply invoke Theorem 9.1.7, which states that when we're looking at this function of n, we can replace the n's with x's, and then think of this as being a function over the entire real number line. And then if you recall, this looks like a problem we've seen previously with L'Hopital's rule. And so what we can do now is simply invoke a previous theorem, 8.6.6, which states that the limit as x approaches infinity of 1 plus r over x to the x power is e to the r. And this was proven back in the section dealing with L'Hopital's rule. Now if you want to verify this again, right here we have it. So just to recall how this was proven using L'Hopital's rule, recall that what we did is this. First of all, notice that this limit here is of the form 1 to the infinity power. And that's because as x approaches infinity, r over x, r is a fixed constant, this will approach 0. And the x up here in the exponent is going to infinity. And so you see this is of the form 1 to the infinity power, which is an indeterminate form. So to prove this with L'Hopital's rule, recall what we did. So to prove this using L'Hopital's rule, the first thing you have to do is put this limit, which is of the form 1 to the infinity power, into the form 0 over 0 or infinity over infinity. And then you can apply L'Hopital's rule. Now to do that, remember what we did is we raised this to the e power. And so recall that, a is equal to e to the ln of a. So we wrote this as e to the natural log of this, and so you end up with this right here. Notice how you drop the x down. When you take the natural log of this, the x can drop down. So right here we have it. And then you can move the limit up into the exponent because this e does not depend on x in any way. And then you're faced with evaluating this limit in the exponent. Now this limit is of the form 0 times infinity, because as x is approaching infinity, well, this is going to infinity. This is approaching the natural log of 1, which is 0. Okay, so this is of the form 0 times infinity. And then you can turn that into one of these limits by just rewriting it algebraically. So right here we have the limit of the exponent. Rewrite this as the natural log of 1 plus r over x divided by 1 over x. Notice this is the same as what we have over here. We just put this x into the denominator, but we had to write it as 1 over x. Now this is of the form 0 over 0, because as x goes to infinity, this will go to 0, 1 over x will go to 0, and as x goes to infinity, the numerator is approaching the natural log of 1, which is 0. Okay. Now you can apply L'Hopital's rule to this limit right here. So we differentiate the numerator, right here it is, and we differentiate the denominator. Right here is the derivative of the denominator. Just off to the side here, recall d dx, the derivative of the numerator. You have to use the chain rule. And then you have to take the derivative of the inside here. Now the derivative of 1 is 0. The derivative of r over x is going to be negative r over x squared. And there you go. That's how you get this term right here. Derivative of 1 over x is negative 1 over x squared. And then this can be simplified as follows. So you just flip the 1 over x squared up, multiply against the numerator, so you see these x squares will cancel basically, and the negatives will cancel, and you get this. You get that right there. Now in the limit as x goes to infinity, this term goes to 0, and you're left with r over 1, which is r. So therefore, this exponent up here is approaching r, or is equal to r rather, since we do have the limit stated there. And so our answer to this problem up here is e to the r. And there we go. And that's how you prove that using L'Hopital's rule. So in other words, when you're looking at this limit, which we originally stated, so here n is supposed to be an integer, and you consider this limit where you just replace the n's with x's, then you can just apply L'Hopital's rule to this, and you get your answer. So basically these two limits here and here are making the same statement, except this one, the n's are relegated to the integers. Now let's consider this theorem. Now let's consider this important result for sequences, and this is called our squeeze theorem or sandwich theorem for sequences. So in this theorem we're given three sequences, a sub n, b sub n, and c sub n. So these are three sequences in which this inequality holds for the sequences. So the ANs are less than or equal to the CNs, which are less than or equal to the BNs, and this inequality must hold for n sufficiently large, meaning that it must hold for all n greater than some capital N, where the capital N is a fixed number. So, for example, this must hold for all little n greater than 10,000, for example, or little n greater than 1,000,000. Then we have this result. If the limit as n goes to infinity of the ANs is equal to L, and the limit as n goes to infinity of the BNs is equal to L, so both the ANs and the BNs converge to L, then of course the CNs must converge to L as well. That makes sense because the CNs are sandwiched or squeezed in between the A sub n's and the B sub n's, right? So if you have this inequality that always holds, and the ANs are converging to L, and the BNs are getting closer and closer to the number L as well as n goes to infinity, then of course the CNs must be getting closer and closer to L as n gets larger and larger as well. Okay, so that makes sense. Now let's take a look at this example down here. Now before we look at this example, let's recall what a factorial is. So n factorial, that's how you read this value. N with the exclamation mark after it, that's read n factorial, is defined to be the number 1 times 2 times 3 times 4 times ... all the way out to n. So for example, 5 factorial is 1 times 2 times 3 times 4 times 5, or 120. 6 factorial is going to be 1 times 2 times 3 times 4 times 5 times 6, or 720. Just notice here that 6 factorial is 5 factorial times 6, right? So in general, you have results like n factorial is equal to n minus 1 factorial times n. Okay, so results like this come in handy from time to time. I just wanted to point that out. Now let's consider this example. So here we want to evaluate the limit as n goes to infinity of 2 to the nth power divided by n factorial. Now, to tackle this problem, let's write out what a few terms look like to get an idea of what's going on here. So first of all, notice that a1, a sub 1, is going to be 2 to the first power divided by 1 factorial. Well, 2 to the first is just 2, and 1 factorial is just 1 times itself, so that's going to be 2 over 1. A sub 2 is going to be 2 squared, or 2 times 2, divided by 2 factorial, and 2 factorial is just 1 times 2. Okay, all right, well, that's fine. We actually see that these 2's cancel here, and you end up with 2 again. Now A3 is going to be 2 cubed, which is 8, divided by 3 factorial, which is 1 times 2 times 3, right, or 6. Okay, well, all right, so that's going to be 4/3 if you reduce it. A to the 4th is going to be 2 to the 4th power, which is 16, right, 2 to the 4th up here, 16, divided by 4 factorial, or 24, right, 1 times 2 times 3 times 4. Okay, well now, let's notice this result. We can actually state that a sub n is always going to be less than 4 over n. Right here we have this inequality. Now how do we get that? Well, take a look at what we have written right here. If you write out a sub n, you see it's going to be 2 times 2 times 2 times 2 in the numerator all the way out to, so you have n 2's up here in the numerator. Right there is 2 to the nth power. And in the denominator, down here, you have n factorial. Okay? Now if we group them in a strategic way, let's notice we can group them like this. The first 2 terms here, 2 over 1 times 2 over 2, that's just 2, right? Of course. The next grouping of terms going from 2/3 out to 2 divided by n minus 1, all of these numbers in here 2/3, 2 over 4, 2 over 5. They're all being multiplied together all the way out to 2 divided by n minus 1. Each of these numbers that are being multiplied together are less than 1. So when you multiply two numbers together that are less than 1, like 1/2 times 3/4, well, that's of course going to be 3/8, you get a number that's also going to be less than 1, right? If both of these are less than 1, and positive, by the way, as well, okay, positive, then when you multiply them together, you're going to get a value that is still less than 1. So all of these numbers being multiplied here must be less than 1. And then the final term, you have your last term tacked on to the end here times 2 over n. So what we have then is that a sub n is going to be less than 2 times 1 times 2 over n. And so that's how we get the result that a sub n is going to be less than 4 over n. Okay, so that's how we get that, just by thinking of grouping the terms that are being multiplied together that comprise the a sub n. Now we can state this. So the a sub n's are always bigger than 0, of course, but they're also always going to be less than 4 over n. We've just determined this part of the inequality. And this one, of course, is true. This piece, of course, is true right here, because, of course, the numerator and the denominator are always positive. So that's going to be true. Now, if we consider the limit of these two bounding sequences right here that bound the a sub n's, we see that the limit as n goes to infinity of 0, well, of course, that's 0, so this is converging to 0. And as n goes to infinity, of course, 4 over n goes to 0 as well. 4 divided by a really huge number is a very small number, so it's approaching 0. So this goes to 0 as well. So therefore, by the squeeze theorem or the sandwich theorem, the ANs must also be converging to 0, and we have our result that the limit as n goes to infinity of 2 to the nth power divided by n factorial must equal 0, and that's it. Now let's note one other thing here that's interesting. So this is telling us that the factorial actually grows faster than this exponential function. And that's in general always going to be true no matter what the base of this exponential is. So if we were to look at the limit as n goes to infinity of even something like 100 to the nth power divided by n factorial, this exponential here grows really rapidly. But the factorial grows even faster, so this limit is still going to be 0. And the reasoning is exactly the same as the way we did this problem. It's just that in this part down here, instead of just looking at these first two terms, you'd have to go out a little further in your expansion, but you could still conclude that 100 to the n over n factorial is still going to be less than some constant k over n. You see over here the k was 4, right? Right down here our k was 4. Well, in this example the k would be larger than the 4, but it would still be a fixed constant over n. And since this goes to 0, as n goes to infinity, 100 to the nth power over n factorial will also go to 0. So it doesn't matter what fixed number we put in here, no matter how large it is, this limit is still going to equal 0. So that tells you that factorials grow faster than exponentials to any base. As large as you want to make that base, factorials still grow faster than exponential functions. And that's an interesting result and an important result to take note of. And here we're going to consider one final theorem in this lesson, and this is called the absolute value theorem. Now this theorem states that if you have a sequence a sub n in which the limit as n goes to infinity of the absolute value of the an terms is equal to 0, then the limit of the original sequence a sub n without the absolute values must also equal 0. That makes sense if you think about it for a bit. If the absolute value of your terms are getting closer and closer to 0, then if we take away the absolute values, these terms must also be getting closer and closer to 0. It's just that these might be getting closer and closer to 0 from the negative side, but they'll still be getting closer and closer to 0. So for example, down here, let's evaluate the limit as n goes to infinity of -1 to the n over n. Now notice that this sequence will generate the following sequence of numbers. If n is equal to 1, we get -1 to the 1 power, so that's -1 over 1, so that's -1. That's when n is 1. If n is 2, we're going to get -1 squared, which is 1/2. Then if n is 3, -1 cubed is -1, right? Divided by 3, so we get -1 over 3. That's when n is 3. Then when n is 4, if we put 4 in here for n, we get -1 to the 4th. Well, that's going to be 1 again over 4. And then the next one, of course, would be -1/5, 1/6, -1/7, 1/8, and so on. And so that's the sequence of numbers that this is generating. Okay, so you can see these are getting closer and closer to 0. It's just that some are getting closer and closer to 0 from the positive side of 0, like 1/4, 1/6, 1/8, 1/10. And some are getting closer and closer to 0 from the negative side, -1/3, -1/5, -1/7, and so on. But to prove that this limit is, of course, going to be equal to 0, we can invoke the absolute value theorem. Notice that if we look at the limit as n goes to infinity of the absolute value of this sequence, well, then we can just get rid of the negative in the numerator, so it's just going to be the limit as n goes to infinity of 1 over n, right? Because the absolute value of -1 to the n is just 1. And of course, as n gets larger and larger, 1 over n is converging to 0. And there you go. And so since the limit of the absolute value of this sequence is equal to 0, the limit of the original sequence without the absolute values is also 0. That's what this part is stating from the theorem right up here. Okay, so that's very simply how you use the absolute value theorem. And we'll need that from time to time